Hi everyone, my name is Dan Kaminsky and I write code. They say that eventually you're supposed to stop writing code. Yeah, I skipped that memo. I'm here for I think my 11th BlackHat, and of course that means Grandma is here for her 8th BlackHat, so most likely she's been... Grandma has been to more BlackHats than you for most values U. And of course, she brings cookies, so there are session cookies. You are welcome to come up after the talk and have some of our secret family recipe. What are we here to talk about today? I've been doing big, important stuff for the last couple of years. Not today. I'm not here to fix authentication today. I'm working on that. Not here to make DNSX scale. I'm working on that too. Today is going to be a return to form. As a community, we've kind of sort of stopped looking at network security. It's an old art of mapping networks, of evading firewalls, of subverting design assumptions. And for the most part, the reason we stopped looking at it is well, look at the attacks. At the end of the day, it's all the same game. Attacker requires a beachhead, SQL inject the web front end, or use a PDF to pop a back end. And then you lily pad. You take your credentials and you go from host to host to host to host to host. And then the important part, you don't get busted. NetSec is only so relevant in such an environment. So it's a good thing that we've moved on to bigger and better things. I don't care. I'm going to look at NetSec anyway because it's a lot of fun. So let's start by looking at something that really kind of seems out of place. Let's start by looking at Bitcoin. Who here has heard of Bitcoin? Very nice. Bitcoin is basically the thing that turns nerd forums into libertarian forums. It's infected everything else in nerddom. Might as well infect my talk. So what is this Bitcoin thing? It's an attempt at making a digital currency with no central bank. There is no Fed. There is no government backing. It's just there, set up by the network. Could say it's a system with economic properties that I know nothing about. I'm not an economist. To be fair, neither are most economists. But the thing that has me interesting as a ye old network nerd is Bitcoin is an overlay network upon the internet that people think has certain properties. Let's see if it actually does. So Bitcoin in a nutshell is based on 3 different verbs. First, transferring money. I, Alice, give Bob 2.1 Bitcoin. So Alice is basically signing this declaration with a public key, signature or stamp of approval. Give Bob money. And then there's gossip. Hey, everybody, Alice just gave Bob 2.1 Bitcoins. Every Bitcoin node in the world is supposed to find this out. And then eventually, one of the many nodes in the world that has found out that Alice gave Bob money is supposed to say, I found out that Alice gave Bob money, and Bob gave Charlie money, and David gave Eric money, and this should be now part of the canonical record of transactions that's occurred. And this is supposed to happen about once every 10 minutes. Now, how do you have millions of computers around the world agree to do something once every 10 minutes? It's actually not that hard. You have them all try to solve a problem, and if someone solves it too fast, and their solutions are coming in more than every 10 minutes, you just keep making the problem harder and harder and harder until you're getting answers on average once every 10 minutes. It's actually kind of elegant, and it's something you do with some crypto stunts. So this is not going to be my Bitcoin talk. I'll be posting some actual Bitcoin slides on dankaminsky.com. But I do want to say the pro and cons of Bitcoin. Bitcoin's really impressive. We're being kind of really presumptuous in the security community about Bitcoin because by all rights it should be totally terrible. See, most code, when you first look at it, it's pretty good, and then you scratch the surface, it's crap. Bitcoin is the exact opposite. It looks terrible when you first see it, and then you go looking for its basic bugs, and they're just missing. I tell you guys, the mark of us is upon this code. So, the quote I say is the first 5 times you think you understand Bitcoin, you don't. Bitcoin has fixed almost all the flaws that aren't forced by the design. That doesn't mean it's fixed all the flaws. The 2 core flaws, at least that I'm going to talk about here, It totally does not scale, and it's absolutely not anonymous. Now, what do I mean by not scaling? If you go to the Bitcoin scalability page on their wiki, it is the funniest document in all of software engineering. What do I mean by that? I'm just going to quote what it takes for Bitcoin to work at large scale. Bandwidth. Let's assume 2,000 transactions per second. Well, we're going to have to move a gigabyte a second. That's actually really bad. CPU, you're going to need 50 cores, 50 CPUs just to participate in the network. And storage, well, a 3 terabyte hard drive only costs $200. You only have to buy a 3 terabyte hard drive once every 21 days. Oh, that's all. So yeah, Bitcoin doesn't scale. It eventually separates out into supernodes and normal nodes. And we have another name for supernodes. They're called banks. Welcome to the new boss. It looks a lot like the old boss. And I'm not saying banks are bad or anything. I got some banks. Peer-to-peer model of Bitcoin eventually dies. And all the advantages that people are claiming for Bitcoin go with it as we are migrated to a bank model. All these hacks of Mt. Gox and everything else, they're basically the beginning of the bankification of Bitcoin. But until Bitcoin does scale collapse, there's an interesting thing we can do. Who here knows Travis Goodspeed? Awesome guy. Travis asked me a great question. He said, hey, Dan, is there any chance Bitcoin could be used as a samizdat service? Samizdat is basically a way of exchanging data without other people necessarily realizing it and getting it all distributed. And this is an old challenge, it turns out. The internet is usually about sending data from point A to point B, and as soon as it's sent, it disappears forever. Is it possible to use the internet to store data and store it indefinitely? Well, if Bitcoin is going to eventually require a 3 terabyte hard drive every 21 days, and by the way, if it's not clear why, because there's no central bank in Bitcoin, every node in the world needs to keep a full record of every transaction that has ever occurred, at least in order to be a full party in the Bitcoin system. So this will eventually take a 3 terabyte hard drive every 21 days if it's going to store stuff mortally. Let's talk about Len. Our community recently lost one of its shining lights. A absolute brilliant mind. He and I collaborated on my 2009 talk along with his wife, Meredith Patterson. If one runs the command strings bytes equals 20 Bitcoin block 0001.dat. Strings is a command that extracts human readable data from any binary blob, even if, in this case, it's 450 megabytes of stuff. We usually use strings to find hard-coded, interesting stuff like default passwords. We're going to run it on the block database of all transactions ever pushed into Bitcoin. If you do that on any Bitcoin node in the world, what do you see? Len was our friend. Len was a brilliant mind, a kind soul, a devious schemer, husband to Meredith, brother to Calvin, son to Jim and Dana Hartshorn, co-author, co-founder, and Shmoo, and BlackHat speaker, and so much more. We dedicate this silly hack to Len, who would have found it absolutely hilarious. And just because Len would have really loved it, Bitcoin is now dependent on an ASCII art version of Ben Bernanke, head of the Fed. So how do we do this? In Bitcoin, Alice gives money to Bob by issuing sort of a challenge. Whoever can sign a message with the public key that hashes the following bytes may claim this money. Well, bytes are bytes. Instead of pushing a hash of a public key, we push 20 characters and only 20 characters of a testimonial. There are some side effects. It does cost money, or at least it costs Bitcoin. That testimonial costs about 1 Bitcoin or $14 because there's minimums to transferring money. This also destroys the money forever. The Bitcoin network is thoroughly convinced that somewhere, somehow, there must be a public key with a hash. Len was our friend, and I am totally okay with that. This is the cyber equivalent of pouring one out for your homies. Can we get higher bandwidth? 20 characters is a little restrictive. Well, Bitcoin does let you send money to a public key directly rather than as hash. So you go from 20 bytes to maybe about 200, 230 bytes. That's a 10x increase. That's kind of cool. But that's not, really massive bandwidth. I want as much as I can get here. I'm greedy. Bitcoin allows for extra data in a signature, in kind of an awesome little bug. See, the way Bitcoin works is you kind of have small programs. The program from the receiver is put this signature and public key on a stack. And the program from the sender is take the signature and public key off the stack and make sure that they're good. All right, well, what if the receiver also puts more stuff on the stack? All the sender says is get the public key and signature off the stack. If there's extra, that's undefined. This is an actual bug you can see in the English just by being pedantic. You can add extra data to any signature, and Bitcoin doesn't complain. Turns out it's not just you as the signer of data who can add data to a Bitcoin signature. Signatures can't cover themselves. In other words, when you sign something, you sign the document. You don't sign the signature that you put on the document because that would be recursive. It's a chicken and egg problem. So if there's extra stuff in the signature, it's outside the scope of what the signature contains. Now, Bitcoin does cover everything in the signature when it's finally set in stone, put into a block, appended to the chain, stored for all time. But there is time between when the transaction goes out and when it hits the actual permanent chain. And in that time, anyone can add extra data, not just the original source. Now, there are some constraints here. Bitcoin has transaction costs that are attached to the size of the data you try to shove into the network. So you get about 1 kilobyte per Bitcoin cent, about every 14 cents right now. So your limits, if you put too much data in, there won't be enough fees to pay for your data. Now, if you're the actual source, you can just pay the fees, so you can have up to 2 megabytes of data in there. If you calculate the block, if you're the guy who does the transaction every 10 minutes, you can totally go ahead and add up to 2 megabytes of data. Because all the restrictions on how much stuff you put into the blocks, except for the 2 meg limit, all those restrictions don't count if you're the guy who does the block. So, yes, Travis, Bitcoin FS, totally possible. And what about anonymity? When people talk about anonymity in Bitcoin or the lack thereof, what they're usually noticing is if I have a transaction and it has all of these complicated looking addresses, 195H8G and 12GJC, first they say, well, it's anonymous because that looks like crap. And then they say, well, okay, it's actually not anonymous because all of these identities on the left side inside the source of a transaction, they're the same guy, and it's really obvious. As for the destinations, there tends to be 2 destinations. One is who you're paying, and the other is who you're paying sending you back change. If you have more money coming in than you actually want to be giving, you just have another transaction where sends stuff back to you. So one of these 2 transactions on the right is all of the guys on the left. Now, if you actually build a big graph of all the identities that come into the Bitcoin network and you link them by, well, did they all show up in the same source, you get graphs like this. And this is from a paper by Reed and Harrigan. And, like most graphs, they look pretty, they're not so useful. I'm joking. These are actually very, very nice. I cut out my own graphs because they got there first. So the problem is linking pseudonyms not actually enough. Reed and Harrigan got lucky. One Bitcoin source actually posted to some forum somewhere, hi, I have this IP address, and this is my Bitcoin ID. Nice job, guy. Another guy actually got, another source publishes the IPs of all the IP identities he gives Bitcoins to. So they're successfully linking pseudonyms to one another inside a Bitcoin, but to actually get at least back to an IP address, they have to go outside and depend on stupidity. The problem is that the published audit trail is noisy and deniable. Reed and Harrigan know it. They're not dumb. So, naturally, much of this analysis is circumstantial. We cannot say for certain whether these flows imply a shared agency in both instances. Absolutely true. They're doing what they can with what they have. Is there another source of data? Well, there are two sources of transactions in Bitcoin. One is the blocks that have been set in stone. One is the loose transactions that would like to be set in stone but have to be distributed all over the place. Both are gossiped around the network. Alice tells Bob and Charlie, Bob tells David and Eric, Charlie tells Frank and Gary. Eventually, everyone in the world knows. This actually works surprisingly fast. Subverting the relay race. This is not actually hard. You just connect to every node in the world. And then the first node that tells you, hey, Alice paid Bob, that's Alice. He done relay it because he done do it. Bonus, you can actually accelerate your own transactions by just relaying them out of rules. You might say, but that might take thousands or tens of thousands of connections. Yeah, computers are a little powerful now, ain't they? So I got a piece of code. It's called Blitcoin. It's an old graphics pun. It does accelerated probing of Bitcoin. Now, how do you discover who you're going to probe? Well, there are three major ways of finding Bitcoin nodes. We can just scan the internet on 8333 TCP. If you've got a lot of bandwidth, that's pretty easy. You can join the IRC channels. It turns out Bitcoin works just like a botnet command and control. You go to LFnet, you join Bitcoin 00 to Bitcoin 99 and the Bitcoin channel, and you just get a running list of everyone logging into Bitcoin. It's very convenient. So I got a little piece of code in Perl called BitBot. I'm pretty sure now Perl is a language designed to write IRC bots. And of course, you can go to any node and say, please tell me all the nodes you know of with what's called a getPeers command. And getPeers just gives you these huge lists of IP addresses. You just get everyone in, I don't know, 20 seconds. Now, Bitcoin doesn't say they're anonymous anymore. And really, they never did. It's a statement from the lead dev on Bitcoin. Bitcoin transactions are more private than credit card or PayPal transactions, but are less private than physical world cash transactions. People are going to be able to associate your IP address with your Bitcoin transactions. So I got into a great conversation with the Bitcoin devs. They're brilliant and wonderful, and they said, hey, can you this is our position. I said, great, I will broadcast it to the world. Now, what about Tor? If you run all your Bitcoin transactions through Tor, all your outbound links will go through some Tor IP, and your anonymity will be equal to whatever Tor's anonymity is, which is not as good as you think. But Tor doesn't do anything about inbound connections. Tor, by its design, only handles some of your traffic, at least under a normal Tor implementation. So if you just sweep the net, you'll actually end up finding a bunch of 8333 listeners that they don't advertise themselves, but there's only 4 billion IPs. There is a bug now filed in Bitcoin to turn off the listener when Tor is enabled. And what about unreachable nodes? Well, you see, most are behind NAT and only connect via outbound links. It means we already have kind of a super node system going on in this peer-to-peer network. The active inbound set is not 50,000 or 100,000 nodes. Right now, it wavers between about 3,000 to 8,000. So, and like as if you were attacking any peer-to-peer network, you just create 3,000 to 8,000 nodes. Actually, you probably need to create maybe a few hundred nodes across the world, put them into the Bitcoin network, and because most nodes can't listen, all the nodes that are outbound only, they take 7 shots. If one of them is you de-anonymize. It's very easy and straightforward. But just how unreachable are these nodes? See, many users are behind wireless routers, and routers implement NAT. NAT is a great system for allowing lots and lots of nodes to share an IP address. Connectivity out is easy, connectivity in is hard. It's a poor man's firewall. Don't mock it, because for years and years, NATs were more effective firewalls than production, very expensive firewalls. Most home routers, though, for their NATs, implement a protocol called UPnP, Universal Plug and Play. UPnP allows nodes on the inside of your network to ask the router to open up ports from the internet. Now, Bitcoin supports doing this by default. So you launch up Bitcoin, it says, hey, home router, why don't you turn on those ports? That'd be great. But let's say it didn't do that. Could we get in anyway? See, here's how UPnP is supposed to work. There's supposed to be a broadcast on your internal network. And that broadcast is supposed to, the broadcast says, hey, everybody on my network, who's a UPnP device? And then everyone's supposed to reply, I'm your home router. Here's where you connect to go ahead and open firewall ports. These are what's called SSDP notify messages. And they're supposed to contain a randomized URL for you to connect to. Not a bad design. So UPnP opens firewall ports. It really should only listen on internal interfaces. These are messages like, hello, router, please let the outside world in. It'd be tragic if routers listened to UPnP messages on the external interface. That'd be like, hello, router, please let the outside world read me on in. Well, crap. Really? Okay, routers are a triple threat. You have the most widely deployed code that is sitting on open internet connections that was written for $40 in Taiwan. How much budget do you think these guys have for security? Crap. I don't want to hear about mobile. Routers are the things I'm worried about. Now, just for stats, not all listeners on 2869 are fully open. Certainly, you need to have fixed UPnP endpoints rather than the randomized ones that the Microsoft stack uses. There are a ton of verified listeners now. We're not, though, talking about hundreds of thousands to millions of hosts on the internet that are sitting in front of home networks that just let anyone knock on the door and say, hey, you should let me in. It goes, okay. We're talking like entire countries have standardized their NATs. So your princess is in another castle. It turns out there's a speaker at DEF CON talking about this very subject, and worse, he found it first. So Daniel Garcia found this in, June of 2010. He's speaking track 3 at DEF CON at 5 o'clock. He's got all the gory details about how UPnP works. And so we've been working together to actually do the worldwide scans to get a more precise number than hundreds of thousands to millions. And for more citing, Armin Hemmel did some great work too. He runs upnphacks.org. He actually noticed that UPnP was exposed to the outside world sometimes back in 2007, but never actually did the scanning to find out how popular it was. So this is still around. It's unfixed. It's all over the place. Welcome, and there's no automated patching. Welcome to router bugs. What about outside the consumer space? I'm sure a decent number of you are from corporate environments. You say, well, we don't really care about Bitcoin. We don't really care about UPnP. We're more about web services and access control lists. Access control lists, what does that have to do with anything? Well, most firewalls, when you really get down to it, they're not doing crazy session authentication and IPsec, because that's all a big pain in the butt. When you actually have two pieces of a corporate network that need to speak to each other and don't want to speak to the outside world, people deploy access control lists. Things that just say, these are the IP addresses that are allowed to speak to me. Access to this IP is constrained to the following range. Well, what about IP spoofing, the old trick? You just send a packet with the source IP of somebody else. Well, you will definitely pass access control lists if you do this. Now, but what about BCP, best practices? They're supposed to stop spoofing. Yeah, they stop spoofing if you're like on a cable modem or a DSL line. You're sitting around with a net connection in like the internet core, you can send traffic as anyone you please. The only place that has really good spoof protection, it turns out, is the cloud. This finally found the one thing the cloud sucks at. If you want to fake your IP address, the cloud is not for you. So is spoofing still effective? Sure, check out this old DNS trick. What, you think I'm going to let all the old magic pass? If you go ahead and you generate a query for some random address at a domain you control, attackerdomain.com, you send packets to all the internet that have this query name, but you spoof the sources to like the 3-byte neighbor and the 2-byte neighbor, the Class C and Class B network, X111 to X1008. if you actually just go ahead and you spoof these neighbors, absolutely the DNS responses are going to go to the neighbors. But in DNS, when you get a request, you need to do another request to figure out, okay, well, what is the address for attackerdomain.com? And that forwarded request, that recursive request, doesn't care if you've spoofed your traffic. That thing will actually keep going on. So granted, this only works for an obscure application like DNS. Who cares about that thing? It only works for UDP. Certainly nothing built for TCP, right? Well, let's talk about TCP for a second. Oh, God, it's so fun being back playing with this stuff. Little remedial stuff. Nomad, you're going to love this. So most modern protocols run over TCP, which is a reliable communication protocol. Before you are allowed to move any data over TCP, we have ye old three-way handshake. Alice sends Bob a SYN, contains a random sequence number. Bob replies with a SYN ACK containing both Alice's sequence number and his own sequence number. Alice replies to Bob with both Alice and Bob's sequence numbers, and data can be sent now. So sequence numbers become sort of a password for all future traffic. If Alice spoofs her IP, the response never gets back to Alice. Alice never learns the sequence number password that she should use. Alice can't go ahead and send data. Thus, IP spoofing doesn't work on TCP. Now, here's the thing. Sequence numbers didn't used to be random. Because, look, if you can, but what happened is we had a bunch of false sessions. People figured out how to inject data into TCP sessions because they were able to guess the password. So said, well, why don't we make the passwords random? Well, the problem is that these things aren't actually passwords. They're sequence numbers. They're things that are there to tell you where in the big stream of data these bytes are supposed to go. If you had this very strange instance where you had two hosts talking to each other, one from port 50,000 and the other going to port 53. Let's say this connection was recycled. Let's say what was called a four-tuple, source IP, dest IP, source port, dest port. Let's say that got reused from one session to the next. There might be packets from the old session. Those packets might show up and be in sequence to the new session. So you get this random blob of bytes that shows up in your TCP connection. Now, TCP is supposed to be reliable, not supposed to have random blobs of bytes. That would end the world. So we have to make sure in this one situation where the source IP, dest IP, source port, and dest port are the same, that we are as distant as possible. We're not random. We're sequential with time. So you have this RFC, 1948. It actually implements this. It says that you should have a sequence number be the source IP, dest IP, source port, dest port, and some secret, hashed plus time. Usually the function that you do the hashing with is supposed to be MD5. So here we have one session. You hash it all together. You get 1, 2, 3, 4, 1, 2, 3, 4. You add time. Now the sequence is 1, 2, 3, 4, 2, 3, 4, 5. If we change one number on that IP address, we go from 2, 3, 4, 5 to 2, 3, 4, 6. Totally different sequence number. But then if the first sequence comes back, time has increased. Look, 1, 2, 3, 4, 6, 2, 3, 4 is definitely after 1, 2, 3, 4, 2, 3, 4, 5. Very nice. Now we got a problem. This is another old problem. What if someone doesn't care about getting into sessions or spoofing anything? What if they just want to see the world burn? So, what if someone just floods us with connection attempts? They don't have to remember all those passwords. They don't even have to use their own IP addresses. But we need to remember all of their crap. And eventually, we run out of memory. This is what's called a SYN flood, and it's older than dirt. Now, what else is older than dirt is the fix. You got a solution called SYN cookies. They were specified, if not invented, by Dan Bernstein in 1999. Closer to invented than specified. I mean, as far as I can tell, he was the guy who fought for these things. Took a while, finally on by default in 2008, coincidentally. This password stops being a remembered password and becomes a challenge. If you can send what I just sent you back to me, I believe you really have control over this IP address, and I'll let you have a session with me. He uses 3/4 of the sequence number, 24 bits, to store the hash of a secret, and the four-tuple, source port, dest port, source IP, dest IP. 5 bits for time, and 3 bits for connection metadata. Now, the connection metadata gives no security. The time gives no security because you can just connect with your own IP and look at those 5 bits, and time is constant for all IP addresses. So you really only have 24 bits of security. Well, what's 2 to the 24? 16 million. Half of 16 million is 8 million. So it is an average of 8 million packets to bypass send cookies. Maybe even less due to fudge factors. Might be down to 1 million. Now, DJB knew this because he's a smart guy. He says no matter what function is used, the attacker will succeed in a connection forgery after millions of random ACK packets. But it's a different reality today than 1999. Sending 8 million packets today, not so hard. A friend of mine just mailed me in today. We're getting a 700,000 packet per second flood, and this is a small one. When you get a forged connection, it can have an arbitrary source, and when you get a forged connection, it can have a payload. So if you have a web service behind an ACL exposed on the internet, someone can just go ahead and send 8 million web services requests in the form of REST or SOAP and get through your ACL. Have a nice day. So you might say, okay, well, I'm going to go ahead and disable send cookies because clearly I need the full 32 bits of security. If an attacker wants to send me 2 billion packets, then fine, I'll notice that. Well, do we have RFC 1948 if send cookies are disabled? About that. Linux is RFC 1948 compliant for the lower 24 bits of a sequence number. The upper 8 bits, no. Those actually are not random. They're actually sequential. They're a counter. It starts with 0. It increments once every 5 minutes. And it's shared between all inbound and outbound connections. So you can actually connect to a host and say, hey, what's the top 8 bits of your sequence numbers that you're going to use for everyone, inbound and outbound? And Linux will just sort of tell you. Now, the number changes every 5 minutes, but so what do? Send a query from your actual IP every 5 minutes or so, just to find the offset, keep updating to find news when it changes, and you blindly spoof sends in a payload containing ACK. So you got to send 2 packets. You got to initialize the session, and then you got to actually acknowledge your way into it. And after 8 million tries, you win. You might say, but Dan, you're gonna run out of connections. You're gonna overload the box. No, I'll send a 3rd packet. I just realized this on stage. This is piping hot. Now I can send a 3rd packet that's a reset, because I know what I sent for the SYN. So I shut down the connection on the server so I make sure that I don't actually SYN flood it. I'm not trying to break it. I'm trying to break into it. There's a difference. Reset attacks. Tony Watson, smart guy, about I think 2005, came up with something called slipping in the window. Resets are a way to shut down a session. Tony noticed that there are only 1 32-bit password required for a reset. In other words, there's a sequence number, an acknowledgement number. Your reset only needs to have 1 of those. And he also noticed that every TCP session has a window. There's a range of values that are allowed for sequence numbers. It can be up to 65 kilobits or kilobytes or 16 bits. He also noticed that this window might even be larger than 65,000. It can have what's called window scaling, where you multiply it by some exponentiation of 2, so up to 8 bits more. So what's happened is we had kind of a resource that was 32 bits wide long. And then we lost a couple bits here, and then we lost a couple bits here, and we end up with, in the worst case scenario, 32 bits minus 16 bits minus 8 bits divided by 50, or 2, 128 packets to kill a random session. Just to kill it, just to shut it down. And he found all sorts of ways this affects BGP. Well, now we're losing another 8 bits because the upper 8 bits are set. So we get 32 minus 16 minus 8 equals 0 bits. And so 1 packet will shut down a session. Crap. It gets worse. Resets only kill a session. And that's cool, but what I want to do is I want to inject into sessions. I want to create the world's most ridiculous cross-site scripting attack. Reset handlers usually only check sequence numbers. That's 32 bits. Acknowledgement handlers, however, check both sequence numbers and acknowledgement numbers. That's full 64 bits of security. You know what 2 to the 64 is? A huge number, an unimaginable number of packets. You ain't getting in. But Alice has a window that might be 16 bits, and Bob might have a window that's 16 bits. So 64 minus 16 is 32. So now we've gone from now we're at 2 to the 32 bits of security. That's, 4 billion divided by 2, that's 2 billion packets. Okay, well that still kind of sucks. But now we add scaling. So that's 5 bits from Alice's window scaling and 5 bits from Bob's window scaling. Now we're down to 22 bits. We're down to 1 million packets for a 50% chance of getting a packet into an established session. Now we go ahead and we add the 8 bits from Alice's predictable high bits and the 8 bits from Bob's predictable high bits. 22 minus 8 is 6. Is it 6? Yeah. Is 6. 2 to the 6 is 64. This actually should be 32. 32 packets give you a 50% chance of injecting into a live session. That's not good. It's not that easy, though, because Linux does go ahead and, in most cases, randomize the source port on a connection. When you connect to, when Alice connects to Bob on port 80, there's a sort for HTTP, for web traffic, there's a source port. And this source port can be anything between 1 and 65,000. Realistically, it's, I'm usually between 20,000 and 50,000 or so. You don't worry about source ports when you're doing an ACL bypass because you control the source port, because it's you who's doing the connection. But if you're trying to inject into someone else's session, well, now you have to worry about the source port. So 6 bits from large windows and a high bit disclosure plus 13 bits with the port leakage leads to 19 bits divided by 2. That gives you 250,000 packets for a 50% chance of injection, even with port randomization. Note that sometimes the TCP client sets its source port. So in DNS or BGP, you'll get fixed source ports. That goes away entirely. But in the normal case, oh no, I have to send 250,000 packets and I get to go ahead and inject data into an arbitrary session. Crap. So what's the status on this? This is extremely old code in Linux. It actually predates the check-in history of Linus Torvalds. Like, this is older than his switch to his present version control system. They are right now figuring out the right fix that doesn't break like 1,000 other things. And there are, in fact, a bunch of potential fixes that would make things even worse, and they don't want to go ahead and have those bugs. I respect that. But I want to do a digression. RFC 1948 is an interesting construction. It gives you sequential and ordered traffic if you got a key. It gives you random and unpredictable traffic without. You can participate in RFC 1948-based sequence numbers in one of 2 ways. You either have a private component, the secret that's mixed in with source port, dest port, source IP, dest IP, or a public component, the ability to read one of the sequence numbers that has been emitted. So you kind of have public and private cryptography with nothing but a password. I mean, that's impossible, right? Okay, well, I'm playing fast and loose with definitions. It's only possible because we're calling public able to see a public packet. It's an intersection of network security. I'm playing games. Now, I want to be clear here. This is a bad idea, what I'm about to tell you. This is an awful idea, what I'm about to tell you. Passwords are terrible. They're constantly being lost and forgotten and stolen. They are responsible for 50% of compromises. They increasingly look like leet speak, which is helping nobody. But if we ignore all that, if we assume we are stuck with passwords, which it is my life's mission to make us not stuck with passwords, but never does it say when you give a talk at BlackHat that what you're saying has to be a good idea. How do we use a password to log into a system without that system learning our password? Well, we've got a couple of solutions out there. Everyone always says, oh, you should hash your passwords in the database. Yet you're still giving the plain text password to the web application who just sees it in unencrypted, unhashed form. Yeah, so you're the bad guy. You just backdoor the PHP form that is taking in the passwords and you log that to a separate file. Wait a week. Are you patient? If there's no salting in your passwords, then someone can go ahead and even have a pre-calculated database. They don't even need to crack the hashes. They just say, oh, it's this hash, that, you know, the password is foobar. So hashes sort of aren't so good. There's challenge response protocols. Send me your version of the password as hashed if I shove this random blob onto the end of it or the beginning of it or something. And we actually have these challenge response systems built into web browsers. So you have a protocol called Digest. You have another one called NTLM. And these things actually, the server never directly learns the password. The server, or, you know, what goes over the wire is a cryptographic exchange. It does, however, require the server to know the plain text password or a one-way version of it. So it's not on the wire, but it's sitting there on the hard drive. I don't think you've won much. And third thing is we require knowledge of the password to go from a cryptographic key pair to a shared secret. These are protocols like SPEAK and SRP. Among many other things, they require the client and server to run some fairly obscure code. Good luck getting either deployed. So, is it possible? I'm not saying, this is not advisable. This is obviously a bad idea. Is it possible to build a system where the client, or only the client, remembers the password, but the server stores nothing but a normal public key? Deploys nothing but a standard challenge to make sure the client has the matching private key. It's just client certificate checking, just whatnot. But the client, the actual user with the password, all he knows is the password. He didn't store anything on the hard drive. In other words, is it possible to construct a cryptographic key pair out of a password? The answer is yes, and as far as I can tell, this is new. Here's how we do it. We do it by answering this question. What vulnerability impacted all asymmetric crypto systems, be they RSA, DSA, or ECC? Does anyone know? Are cookies involved if you know? They're really good. Come up and get a cookie. That is exactly right. The Debian bug affected every asymmetric crypto system. I am so happy someone in the audience knew. Awesome. The problem in Debian is the entropy that was generated was always the same. All asymmetric crypto systems use entropy as follows. Grab some random bits and permute them. Change them around until they meet the requirements of your public-private key system. So predictable entropy leads to predictable key pairs, be they RSA, DSA, or ECC key pairs. It just works. So what if we make it not a bug? What if we make it a feature? See, cryptography is all about constructions. We have hash functions that fingerprint data. We have stream ciphers that make a stream of data. We have block ciphers that mix a bunch of data with a key. It turns out you can construct all of them from each of the other. Well, we also know how to take a password and turn it into a stream of pseudo-random number generators. We call this a seed to a pseudo-random number generator. We can even do this in a way, in a very special way, that is both time hard, which means it takes a bunch of CPU, and memory hard, which means it takes 256 megabytes of RAM to derive what the stream is going to be. And we have great code that does that. It's called scrypt. So what if we just make the output of scrypt's random stream the input to RSA, DSA, or ECC? Well, you would end up with a 2048-bit RSA key pair with a trap door in the form of a password. This, my friends, is not even close to theoretical. Here's a normal use of SSH key gen. If you notice, I generate keys 3 times, I output to a random file, and I get 3 different keys, which is what you would normally expect. But now we are going to use a special thing called an LD preload. LD preloads are basically library preloads. They change the rules of the universe for whatever is run underneath them. So we have a little piece of code I've written called Fidelius. Fidelius, and I'll explain why it has this name in a moment, So we load up Fidelius, and we say that the password for what we want to generate our stream for is my grandma. We generate keys. We do it once, ADOD522A. We do it again, ADOD522A. So now all of a sudden SSH keygen is making the same key from the same password. So why do I call it Fidelius? Fidelius is a horribly nerdy name. It is based on the concept of Harry Potter. Harry Potter, properly understood, is the story about the epic consequences of losing one's password. Really is, and if you don't understand it, go find a nerd. Fidelius is how passwords fail in the Harry Potter universe, so I went ahead and thought it'd be funny to name this after it. I mean, it's really a bad idea. Fidelius hooks dev-random, dev-urandom, OpenSSL's random functions, and a few other tidbits to go ahead and basically say, instead of having actual entropy, have something based out of what comes out of scrypt. 1 second processing time, 256 megs of RAM is the default. If you are going to try to brute force passwords through Fidelius, you're going to have to do this much work per attempt. So no 440 million passwords per second GPU fun for you. You can also go ahead and seed with a file as well. So this works. I mean, this is not like a theoretical funny thing. Like it gives you generic multi-application support for predictably generating key pairs from passwords. SSH keygen will consistently generate SSH keys. OpenSSL will consistently generate certificates. You can even have a CA sign a password. How crazy is that? And Freebird, my DNSSEC client, our server, will generate consistent DNSSEC keys off of nothing but a password. Allows message signing, message encryption, client certificate authentication with nothing but a password. There's no server-side changes. The server has no idea there's a trapdoor. So we have effectively solved the login with the password without the system learning your password problem quite thoroughly, without you having to store anything more than stuff in your head, which we know is hard. Kind of cool, in Bitcoin, you could literally give money to a word or a photo. And there's no pain server side. All the time, memory, hard requirements are limited to the client. The server just does client-cert authentication like it always has. That's kind of cool. It's totally standard crypto. In fact, the server doesn't even know that a password is involved, and would probably freak out if it did. So, primary issues with Fidelius. I'm a crypto guy, and obviously I know this is a bad idea. The obvious ones are that it uses passwords, and passwords tend to have low entropy, and passwords tend to be forgotten, and passwords tend to be leaked. But there's some not obvious ones. This is a fragile scheme to the nth degree. An explicit scheme would use a password to seed. An explicit scheme standardizes everything. Says not only am I going to use the dev random, but here's what I'm going to do. Here are the parameters. Here's how sure I have to be this is a valid prime, and so on. As an implicit scheme, we are dependent on all these non-standardized factors that happen to be in SSH keygen 5.3p1. So you have to regenerate your keys with the exact same code, and that's sort of painful. You also can't really salt. You don't have a random blob to store somewhere and check against. I had to strip that out of scrypt. Because the only thing that the user remembers is their password, and no extra space is available. So what that means is all certificates that are generated with the trapdoor password are the same certificate, and you can tell. You can rainbow table that. Now, you can only build the rainbow table 1 second at a time, but you can still do it. So how would you actually do salting with a Fidelius approach? The basic idea is that the private key is not merely computed from the password. It's a combination of the public key, which is public, so you should be able to get it too, and the password that you're keeping in RAM, in your memory, excuse me. The public key is then the carrier of the salt. This works well for protocols like SSL, where you actually get the public certificate before doing any sorts of proof of possessing the private. It fails utterly for things like PGP, which, if you want to try to encrypt mail to a public key that's backed by a password, if you want to sign something with a private key that you got from a password, you don't know the public keys that people have out there. The certificates, the public keys, are also a good place to hide parameters, like, hey, scrypt only needs to be this secure because the actual password has a bunch of entropy. So that's just sort of the deal. But let's get back to TCP IP. Let's get back to straight up packet tricks. Let's talk about one last thing we can do with networks. Who here has been paying attention at all to network neutrality? So there's a very interesting question. Will our networks actually start inspecting all of our traffic and giving us different quality of service based on how valuable they think this traffic is to us? There are two kinds of neutrality violation. There's the totally obvious stuff. We block this website. And then there's more subtle things. What I'm about to show you is basically code that will find biased network policy no matter how subtle the violation is. The bias is, excuse me. What does this mean to you? If biased networks are affecting you, here is your proof. And if you are biasing your network, there's a horde of people who are about to be able to generate proof. So you might want to stop doing that. So let's look at our standard network topology in the real world. You got a client, it's got a home router. Home router talks to an ISP. The ISP has links to, this network and that network. And through one of those networks, you get to Google or Microsoft or Yahoo or BlackHat or whatever. Now that ISP is sort of a choke point. If you put something nasty there, well, it's going to be able to get in front of all of these links and affect and slow down and accelerate or change whatever the heck it wants. So the fear is this. There will be a magic box that is deployed within ISP networks in front of all the links. The box matches packets to policies that apply different sorts of rules. Now these policies can be stateless. Do I like this packet? Or they can be stateful. This packet is part of a flow. It's part of a group of packets. Do I like this flow? And if not, what am I going to do to the packet? Now the policies can be anything, and they can do anything. You're talking to Yahoo, we're going to limit the maximum bandwidth. You're talking to Google, we're going to increase the minimum latency. You're talking to anyone at all that has an advertisement, we're going to change the advertisement. The problem with the subtle changes is, let's say Bing.com is 50 milliseconds slower than Google.com. Is this because of the ISP? Or is this because Google.com has better hosting? Who knows? There's 15 routers between you and Google, and a different 15 routers between you and Bing. And who knows which of those routers is overloaded? So you get kind of plausible deniability from the ISP side. What we need is normalization. Whether the tester is accessing Bing.com or Google.com, the network path should be identical, or at least uncorrelated with identity. We call this normalization. It doesn't matter who you're connecting to, you're using the same route. So if there's any difference in performance, it is because of the particular same route that you're on, most likely a policy box at the ISP. So let me give you the simplest possible way to do normalization. If you just look at HTTP, this is freaking cake. Policy says all flows associated with an HTTP request to a host www.bing.com should be delayed by 50 milliseconds. I guarantee you there are boxes that are doing this today. You want to detect them, configure a single server to accept HTTP requests for Bing.com, Google.com, and so on, and actually service those requests as if you were Bing, as if you were Google. You don't even have to write any code. We have a name for these things. They're called proxy servers. HTTP has explicit support for doing this, and there's been code to do this since the beginning of time, pre-NAT. And then the rule is, if the traffic from the proxy server is faster for Bing than it is, or is faster for Google than it is for Bing, you've just detected an HTTP biased policy. It has to work. There's a problem, though. First, it's protocol dependent. HTTP can be made to do this for very low work, but there's a lot of other protocols besides HTTP. Other protocols require lots of work to implement and emulate. Now, you can do this, but it's a big pain in the butt. And the larger issue is who says you'll actually see the policy in the first place? You've got some IP address. You're, I'mAwesomeTester.com. You know what the policy engine does? Just says, I don't slow down, IamTester.com. How you doing? So it doesn't matter how many hundreds of test servers you have if the policies are only applied to genuine Bing.com or Google.com addresses, which you can sniff DNS to find out. So I've written a solution, and it's called Neuter. What? It's the neutrality router. Who here knows what a VPN is or has ever used one? All right, so VPNs basically give you an encrypted tunnel to somewhere else on the internet, and all your net connections go through that somewhere else. To break it down even further, you have a client. Traffic from your client is encrypted and is sent off to a broker, or as we call it in the field, a VPN concentrator. The broker has an IP address, and it goes ahead and that IP is what contacts Google and contacts Microsoft and contacts Yahoo. And all responses from Google, Microsoft, and Yahoo go back to the broker. And the broker takes that packet and encrypts it up and sends it back to the client, who then goes ahead and says, oh, I sent a request, I got a response, all is great in the world. And my IP address is the IP from out in, VPN land. We cool? We understand how this is working, and that you're encrypting your connection and having someone else be your IP? Here's what we're going to do differently now. This is a fun little stunt. Instead of encrypting traffic from the broker to the client, we just send the traffic back to the client in the clear, wide open. Anyone can see it. In fact, we don't even use the broker's IP address. The traffic that goes back to the client, it looks just like it really came from Google, Yahoo, Microsoft, wherever. We spoof the source. Now, why would we go ahead and do this? Why would we let the ISP see all of our traffic? Well, we want them to see the traffic. We're trying to trigger ISP policy. We're trying to trigger the response that would normally be reserved for IP addresses at Bing or Google, and we want them to apply to our nice normalized path neutrality router. The policy engine can't tell the difference between Google and Bing in the router because we've spoofed the source. We're lying. Traffic took the same path. Traffic came from the same source. Why are we seeing different quality of service? Gotcha. So, there is a bug, though. There is a thing the ISP can do. The policy engine in this case, yes, it sees the traffic from the server to the client, but it does not see the traffic from the client to the server. That remains encrypted VPN style, or sent over some other link like a clear wireless link or a cellular or whatnot. What if the ISP just, didn't trigger the policy if it didn't see both sides of the conversation? This might actually be the default mode. Well, you do that. Check it out. We got normal neuter, and normal neuter spoofs the server to the client. We also have a roto-neuter. Roto-neuter spoofs the client to the server. Why would we possibly do this? Well, check this out. Yes, there's the path from the client to the normalized router, but there's also the path from the client to the real Google. I show you two samples of TCP traffic. In one sample, the client is talking really to the true Google. ISP sees everything. It's like nothing was even there. And in our next sample, we go ahead and we tunnel just the traffic from the client to the server to the broker. ISP sees nothing. And then the broker goes ahead and spoofs the client to the real Google. So Google sees this packet, it shows up, it comes from the client, Google replies. So what this means is that the ISP in this case has seen a half flow. It doesn't see the client's traffic to the server, it only sees the real Google's responses to the client. Both samples have the same path for server to client traffic. It's the actual Google to client path. If they were to have different performance characteristics, it must be because of the network that no longer sees the client traffic. It must be the ISP. So it's the catch-22. If the ISP applies traffic to half flows, I see it when the client receives the fake Google flows from the normal neuter. If the ISP applies the policy very carefully only to the full flows, I see it when the client receives real Google flows because of roto-neuter. So either way, either policy, I see it, and I see it differentially. This is the end game. Biased policies might as well be transparent because they're sure as heck not going to be deniable. However, I am a greedy bastard. I don't like the fact that my normal neuter doesn't see all the traffic or doesn't fully correctly emulate everything. How do I fully correctly emulate everything? Suppose I want to see the ISP. Suppose I want the ISP to see the full bidirectional traffic. Why do I want this? It is guaranteed to trigger all policies. It also opens up listeners inside of NATs that might be inconveniently placed in front of my link to an ISP. Because if you have a NAT, it opens up return ports only when it sees outbound sessions. In this situation with the half VPNing, there's no outbound session. So the NAT's blinded. And if the NAT's blinded, that means all those spoofed server-to-client responses don't get through, and we don't get to have any fun, and that's a sad day. So, advantage, we really do want to see the ISP to see bidirectional traffic if possible. The disadvantage, if the client successfully sends an outbound packet through the NAT, and if it gets out through the ISP, you know where it ends up? It ends up at the server. Server's sitting there like, hey, I just got a request, or I just got a packet in the middle of a session. What the heck is this? I better respond. I better interfere with whatever weird stuff the other router is up to. And so that's kind of painful. How do we get around that? How do we make it so when the real server receives traffic, it ignores it? Well, the easiest thing to do is just use a bad TCP checksum. That's right, we're screwing with checksums. Client can go ahead and tunnel its valid traffic to the broker. The broker can go ahead and say, oh, I've got packets for Google, Microsoft, Yahoo, and those have real TCP checksums. But then there's a second stream, and it's really coming from the client network. And this stuff on the client network goes out the NAT, and it goes out the ISP, but it's got a bad TCP checksum. So it gets all the way over to the destination. The destination says this has gotten corrupted along the way. I'm going to drop it silently. Advantage? It's definitely going to be ignored. Server's not going to care, not going to respond. The NAT will most likely let the session through. And the policy engine might ignore the TCP checksum. The problem, though, is there's a lot of mights there, right? Like the policy engine could check the checksums, and the NATs might go ahead and fix the sums. But there's another catch-22 here. If policy is disabled when checksums are bad, then all I do is I have the client sending bad checksums and the broker sending good checksums. And if the network mysteriously speeds up, that means there's some box on the network that is looking at the checksums to decide whether or not to apply policy. So hey, I still win. Let's try another trick, low TTLs. When you send traffic on the network, you can control how far it goes. You can set what's called the time to live. So a client can send traffic to the server with a relatively low TTL. It can go as many hops as to get past the NAT, and it can go as many hops as to get past the policy engine, but it can't actually reach the server. The advantage is what you're sending is legitimate traffic. There's no corrupted checksums, and sending traffic with low TTLs is fairly legitimate behavior. The problem is that the policy could be set up to note the existence of a low TTL and disable itself, to try to cloak. And the router may drop sessions if there's ever an ICMP time exceeded message. It does say a session is dead. And it kind of sort of represents a denial of service attack against routers because they have to have their actual operating system send these responses. But we've got another catch-22. See, if the traffic is if speed increases when I send traffic with low TTL, I can differentiate policy that cares about TTL and thus exists, and policy that doesn't care about TTL. More importantly, and this is actually kind of funny, I can probably tell you at which hop the policy engine is, based on whether the actual policy is triggered or not. So that's actually kind of amazingly cool. I can tell you, oh yeah, there's a filter, and it's at this hop in the ISP. Or at least it's 5 hops away. Strategy 3. This is called being a perfectionist. Nobody says that a server absolutely needs to respond to traffic that is not associated with sessions that exist. It's supposed to by RFC, but no one says it has to. A lot of hosts on the internet actually want to know if they're being filtered by ISPs. And more importantly, a lot of hosts are behind firewalls. And firewalls commonly have this very cute policy that says, this is not part of anything good. I should drop it on the floor. Now I've earned my paycheck. So security is going to help us out here. We can have a client set up a totally legitimate 3-way handshake. Client sends to Google. Google SYN acts to client. Client acts to Google. There's a real session there, and the ISP has totally seen it set up. But now, guys, broker is going to snipe that session at the server. It's going to send the reset. It's going to cut it off. The ISP can't see the reset because that's happening on the big old internet. So what does the ISP see? There's an open connection. There's an open link from the server, or to the server and from the server. It's bidirectional. Client's got an open link. ISP's got an open link. It's only the server that thinks everything has been shut down. Now we have the broker go to the server and set up an actual connection to Google, Yahoo, Microsoft, whatever. It sets up the connection. It's got something live with its own 3-way handshake. It splices the data flows from its own session into the existing open session at the client and ISP. What does this mean? It means the client can talk to Google, who will ignore all the traffic because it's not part of a legitimate session, and broker can impersonate Google replying back, which will get through and trigger all policies because it's part of a legitimate session. Client talks to server, server talks to client, ISP is happy. You can't explain that. 100% perfect bidirectional flow. So there's a bit of warning. If you are out there and you are passively monitoring network traffic, be aware this does mean that a really intelligent malicious client can make you think that any IP address in the world is saying anything. It's like, yeah, that's a nice TCP dump you got there, pretending that Google is giving me, all sorts of very spicy images. Unfortunately, that's not actually that IP. You can detect this, right? Like there's all sorts of things that have to be done to make this possible. So if you are monitoring passively and assigning, content to IPs, hey, validate checksums and check TTLs, and watch out if the server ignores acknowledgments that are not part of an established session. So where Neuter is now, it emulates half flows at present. It's extremely fast. I'm actually, did anyone here ever use my old Paketo Kiretsu code? Yeah, so Paketo's coming back. This is written to libpaketo. It supports anything that runs over IP without having to write any code at all. If you want to know whether an ISP prefers Xbox 360 traffic to PlayStation 3 traffic, Neuter will totally tell you. It's just an ISP that exposes traffic and sees if it's any slower. So in summary, after this big sprawling talk, networks are neat. Bitcoin, totally not anonymous. Great for storing data in, though. UPnP sometimes exposes itself to the outside world. ACLs can be bypassed using some interesting sequence number tricks and large numbers of packets. Passwords can, in fact, be used to seed asymmetric crypto, though they probably shouldn't. and subtle net neutrality hacks are absolutely doomed, absolutely detectable, transparency or bust. So that's what I got. And by the way, if you want to do some release engineering for me, I could use some help. I hope you enjoy.